Hello and welcome to our lesson on implicit differentiation. So to end this module, we're going to look at a third set of word problems, but before we can attack those, and it will be, kind of similar to the other two sets of word problems we talked about, but we need another skill set, and that is what we call implicit differentiation. So we've learned all kinds of derivative rules, but all of the rules that we've used, we have applied to differentiate explicit functions. Those are functions that are defined where y is defined in terms of x. And so today we're going to talk about functions that are not defined in terms of where one variable is not defined in terms of another, and how do we differentiate if these variables are all mixed up in one equation. Okay, so let's start out with some terminology and then I'll show you where we're headed. So we know a function is a relation between two variables, and that relationship is such that every input into that function corresponds with exactly one output. So graphically, we know that a function, passes the vertical line test. Now, if that function is explicit, which is what we have been dealing with thus far, it means that one of the variables is defined in terms of the other. So you see one variable like y defined as 5x plus 2. So y is defined in terms of x, or y equal to x squared minus 2x minus 3, again means y is defined in terms of x. Or we have x equal to 4y plus 1, means x is defined in terms of y. And the same thing here, you have x all by itself defined in terms of y here as 10 divided by y. So an explicit function, again, one variable is defined in terms of the others. In terms of the other just means you have one variable isolated, and the definition for that variable, or what it's equivalent to, is an expression containing the other variable. Okay, so you have one variable by itself on one side, the other variable in an expression on the other. So if you have an implicit function, implicit functions are defined by both variables. You're going to see both variables together on one or both sides of the equation. So you have x and y together here equal to a 12, or x squared, 2y cubed, 4 all together on one side equal to 2. Again, if you have both of the variables together on one or both sides, you don't have one variable defined in terms of another. You have, again, what we call an implicit function, and we need to be able to differentiate implicitly, because it's sometimes not possible to get our function to be explicit. Okay, so in differentiating implicitly, or differentiating functions that are implicit, basically is going to require the chain rule. So just want to refresh our memory here. If we were differentiating with respect to x, that's what this is telling us to do here, we know the power rule. We would say that this would be equal to 3 times x now to the second power. So we multiply by the exponent, then subtract 1 from the exponent, right? Now as soon as x changes to anything else, like 5x minus 7, or whatever we want to put in that parentheses, we're still differentiating with respect to x. We're still going to apply that same power rule. So we would have 3 times, instead of an x, we have a 5x minus 7, and then we would subtract 1 from the exponent, so it'd be squared. But again, as soon as this changes to anything other than x, we have to multiply by its derivative. So in this case, we're going to multiply by the derivative of 5x minus 7, which would just be a 5. And then the chain rule, that's using the chain rule. That's applying the chain rule to that specific situation. But the chain rule we can use to generalize. As soon as the thing that's being raised to the third power is anything other than x, we're still using our power rule, but then multiplying by that derivative. So in this case, if I was differentiating with respect to x, u cubed, again, 3 times u squared, still using that power rule, but then we would have to multiply by the derivative of that thing that's no longer just an x. Now because it's generic, we're just going to say it's the derivative of u with respect to x. Okay, that's generalizing the, using the chain rule to generalize the power rule, right? And then the same thing here. So if it was a y instead of an x, or a u instead of an x, or a 5x minus 7 instead of an x, we're still going to use our power rule. So the derivative with respect to x of y cubed would be 3y squared. And then because, again, this is not an x here, we have to multiply by the derivative of this thing, which would just be called dy dx, the derivative of y with respect to x. Okay? And here, we could have said the same thing in this one. I could have said the derivative with respect to x of 5x minus 7, right, instead of a y or a u. But I know the derivative with respect to x of 5x minus 7 is just going to be 5, and that's why we actually have a derivative there. And that's why we have something more generic here and generic here. Okay, but we're differentiating the same way we normally differentiate when we have other variables. Typically what we're going to see is y, but because it's not just an x, right, we're multiplying by the derivative of that thing. So when we go to differentiate implicitly, and you have x's and y's together, it's all the same differentiation rules. We're still using power rule, product rule, quotient rule, all the same, okay? But what you got to be careful with is if you're differentiating a term that has a y in it, because it's not an x, when you differentiate with respect to x, you will always have to multiply by a factor of dy dx, always, because that's the derivative of y with respect to x. It's like the derivative of that inner function. It's using our chain rule, okay? So hopefully that makes sense. So one other thing I want to point out is when you go to differentiate, when you're taking the derivative of a function, if it's an explicit function, then you get an explicit derivative. I can't spell. Okay, so if you start with a function that's y equals something over here with an x, then when you take your derivative with respect to x, then you're going to get 2x over here, again, something explicit. So y is defined in terms of x squared, and dy dx is defined in terms of 2x. So if you differentiate an explicit function, you're going to get an explicit derivative. So just a y here, just a dy dx here, just x over here, just x over here in the derivative. Okay? If you are going to differentiate an implicit function, you are going to get an implicit derivative. So if you're differentiating something that has x's and y's together, your derivative will have x's and y's in it. Okay, so I want to show you how we're gonna, like a little preview of differentiating explicitly versus implicitly with this particular function, x times y equals 10, because that's an implicit function, but it's really easy to make it explicit. If I have x, y equal to 10, I can easily just divide x over and call this y equals 10 divided by x. And then actually I can call this y equals 10x to the negative 1. So now instead of an implicit function, I have an explicit function, and I can differentiate this the way I normally would. So if I wanted to differentiate now, I'd say y prime, or because we're going to be doing work with implicitly, and we'll have lots of terms with y's, instead of using y prime and confusing that with an exponent, I'm going to stick to the dy dx notation. Okay, but that's just the derivative of y, right? Derivative of y with respect to x would be equal to negative 10x to the negative second, or we could call that negative 10 over x squared. All right, there's our derivative of y with respect to x, negative 10 over x squared. So in this case, we started with an implicit function, but we made it explicit and then differentiated the way we normally would, and we ended up with an explicit derivative here, just in terms of the one variable x. Now, if we wanted to not rearrange our function, just differentiate it the way it is, then we would have to do so implicitly. So if I wanted to take the function as is, take the xy equals 10 and do my derivative, take my derivative as is, then this would be a product rule problem, where this would be one function multiplied by a second function. So I'm going to call this f and g here. And I know that I'm going to be using my product rule, which is f prime g plus f g prime. So my derivative of my derivative of x would just be 1. And I'm going to multiply by g, which is y. And then f, which is just x. And then my derivative of g. When I take the derivative of y with respect to x, it'd be just like taking the derivative of x. The derivative of x would be 1. So the derivative of y is going to be 1, but because it's not an x, we're going to multiply by dy dx. So it's not just 1, it's 1 dy dx. Okay, and then equal to, on the other side, we're going to differentiate the constant here, and the derivative of the constant is just going to be 0. So now if I want to actually solve for my derivative of y with respect to x, which is generally the goal, right, is to find our derivative dy dx, I have to do a little bit of work here. So 1 times y, that's just y. I'm going to subtract that term over. So I have x times 1 times dy dx, which is just x dy dx left on the left, and then on the right, again, I'm subtracting this term over, subtract the 1y from both sides. So I'm left with a negative y here. And now I can, because this is being multiplied, divide both sides. So divide by x here, divide by x here. That's going to reduce out of that side. And so dy dx is equal to negative y over x. So now we have 2 different versions of our derivative. Over here, we're saying dy dx is, let me just write this one more step. Over here, we're saying dy dx is negative 10 over x squared. So that's one version of our derivative. And then over here, we're saying dy dx is negative y over x. That's a second version of our derivative. One is explicit, only has an x in it because we differentiated the explicit version of the function. And then over here, we have an implicit version, where our derivative has x's and y's in it because we differentiated the implicit version. Now they look different, they definitely look different, but are they in fact any different? So at this point, they're definitely different. But remember, the point of what we're doing when we're finding derivatives is we're looking for an equation to find the slope of a tangent line at any particular point. Well, let's go ahead and look at the slope of the tangent line at the particular point we're given here, which in this case is going to be 2, 5. At 2, 5, what's happening? Well, if I wanted to evaluate here at 2, 5, I'm going to plug in 2 for x, 5 for y. Well, there's no place to plug in a y because this is explicit, so I'm just going to plug in the 2 for x, and I would get negative 10 over 2 squared, which would be negative 10 over 4, which reduces to negative 5 halves. So the slope of the line tangent to this function at that point of tangency 2, 5 would be negative 5 halves. Okay? So over here we have a different looking derivative, but again, if I evaluate this at the point 2, 5, I'm going to plug in 2 for x and 5 for y because both variables are in my derivative, and I'm going to get a negative 5 on the top and a 2 on the bottom, the exact same slope. So even though those two derivatives look different because one's explicitly in terms of x and one's implicit in terms of x and y, it is going to lead us to the same slope at any particular point of tangency. Okay? Now this process over here, differentiating explicit functions, we have lots of practice with. So that will not be the focus of this lesson. I just wanted you to see that we have options most of the time, but we want to practice this because it won't always be possible to take our function and rewrite it explicitly. Sometimes we're stuck with this implicit version and we still have to be able to differentiate. So when the function becomes a little bit more complex, what do we do to actually work on that differentiation? We're using the same rules, it just looks a little strange because multiple variables are together. So let's talk about some steps and then we'll try it out. When we're differentiating implicitly, so we have an implicit function, we're not going to manipulate it in any way, we're just going to take its derivative. What do we do? So differentiating both sides of the equation with respect to x, that's what we're doing, right? We have to remember that when we do this, it's the same product rule, same quotient rule, it's the same power rule, all the same differentiation rules, but any term that we differentiate that has a y in it will have to be multiplied by a dy dx because basically our chain rule, right? We're differentiating with respect to x, we're using a rule that we normally apply to x because this is not an x, we multiply by its derivative. Okay, so basically that's happening because of the chain rule. So once we've done this, all the differentiation rules, and we put in our dy dx wherever it needs to be, it's possible you end up with multiple terms that have a dy dx, and you're going to try to solve for that because that's what we want. We want a derivative of y with respect to x. And so we're going to rearrange our equation. Rearrange all of the terms so that any of the terms that have our dy dx in them, they're all on one side, and anything that doesn't have a dy dx is going to go to the other side. And then everything on the one side that has that dy dx, because they have that in common, we're going to factor. So factor out the common dy dx that you have on the one side, and then you should be able to divide to finish solving. So divide to solve for dy dx. That's your derivative, and then if you need to evaluate it at a particular point of tangency, then we'll be able to do that. Okay, so we're going to differentiate implicitly. We're not going to take our function and manipulate it, although sometimes we could. It's not wrong to do it because we need the practice. We're going to differentiate implicitly our implicit functions in the form they're given. Okay, so let's try this one. If I want to find the derivative with respect to x of this function implicitly, that means I want to leave it in terms of two variables. Now, I know I just said let's not manipulate the function, but I could actually take one step here that would still leave us with an implicit function, but it would make our life a whole lot easier. If we wanted to differentiate this as is, I could absolutely use my quotient rule because I have one function divided by another. But if I just make this side a proportion and cross multiply, then I have x minus 5y as my one cross product, and then 2x plus y as my other cross product. Then I have still an implicit function and much easier to differentiate because it's no longer a quotient. Okay, so a manipulation that still leaves you an implicit function for the purposes of our practice would be totally fine. Okay, if you wanted to use quotient rule, it's fine, but that would be a much longer process, I promise. So let's try this one. Let's differentiate with respect to x now. So when I take the derivative of each of these terms, right, it's still our sum and difference rule. I can take the derivative of each of these terms separately. So the derivative with respect to x of x is just going to be 1 minus, if this was a 5x, it would be a negative 5, right? So it's negative 5y, which means it's negative, again, if it was just negative 5x, our derivative would be negative 5. Because it's negative 5y, it's going to be negative 5 again, but it gets a dy dx. So we're doing the same rule here, but as soon as this changes to something other than x, like a y, we got to multiply by its derivative. So the derivative of negative 5y is going to be negative 5 dy dx. And then the derivative of 2x is just going to be 2. And the derivative of 1y would just be 1, and then a dy dx. So anything with the dy dx we want on one side, and anything without we want on the other. So what I'm going to do is move a couple of my terms and rearrange my equation a little bit here. I'm going to move this term to this side by adding it over, and I'm going to move this term to the other side by subtracting it over. So I have on the left here the 1 minus 2, and on this side I have the 1 dy dx plus I brought over the 5 dy dx. Okay, and I'm trying to solve for dy dx. So I have on this side two terms with a dy dx in common. I'm going to factor that out. If I factor out dy dx, I'm going to be left with 1 plus 5, which is going to be, oh, this should be a negative 1 here, which is going to be 6. So the last step to solve for dy dx, which is being multiplied by 6 now, is to just divide that 6 over. So we're going to say, as one last step here, that dy dx all by itself is equal to a negative 1/6. And that would be our derivative. Okay, now if we had to evaluate this at a particular point, you can see from our derivative that it doesn't matter what x or y is, that slope is always going to end up being a negative 1/6. We're going to end up with a constant slope for our derivative. And there are other ways to do this. You can have other forms of your derivative look a little different, but I think the path of least resistance to differentiate implicitly with this example is what you see here. Okay, so there it is. And if you arrived at something, if you tried this another way, like using your quotient rule, you arrive at something different. The best way to determine if it's correct, if your work is correct versus someone else's work, or like what like what my work says, or if you're using technology to find other types of answers, like how are these things correct, and just pick a point of tangency, plug it into the multiple forms, and make sure that your slope ends up being the same. And that'd be a way to verify, okay, if that makes sense. So let's try another one. We're going to find dy dx here. Let's leave this one in its form as it is. Let's not do any manipulations and just try to differentiate. So if we're going to do that here, this is a product of two functions, right? We have a product of x and y squared, and then this is a product of two functions. We have a 4x being multiplied by a y, so we're going to have to use our product rule twice here. So I'm going to say f and g here. So it's going to be f prime, which would be 1, times g, which is y squared, plus f, which is x, times g prime, so the derivative of 2y squared with respect to x, of y squared with respect to x would be 2y to the first, and then we have to multiply by a dy dx. Okay, so that's the first one. So this guy, that's all this right here. Okay, now I'm going to use my product rule again, but for this product. So I have f prime g plus fg prime. So f prime, the derivative of 4x, would just be 4. That gets multiplied by g, which is a y, plus I have f, which is 4x, times g prime. So the derivative of y with respect to x would just be a 1, and then dy dx. And that's going to be equal to the derivative of our constant is going to be 0. Okay, so I want all of the terms that have the dy dx to stay on one side of the equation, and everything without to go to the other side. So what I'm going to do now is leave this term here and leave this term here, and then I'm going to subtract the other two terms to the other side. So this one's going to move, and this one's going to move. Okay, so I'm going to have a 2xy. Let me just change colors. How about green? 2xy dy dx, that term's going to stay. Plus I have a 4x dy dx, that term is going to stay. And again, I'm going to subtract these two terms over. So on the other side, I'll have a negative y squared and a negative 4y. And now because these two terms both have that dy dx in common, I'm going to factor it out, which will leave me the 2xy and the 4x. And it's still equal to negative y squared minus 4y. And then lastly, if I want to solve for dy dx, right, find my derivative of y with respect to x, it's being multiplied by this binomial, so I'm going to divide it over. So dy dx is going to be equal to a negative y squared minus 4y, all divided by 2xy plus 4x. And we did it. Okay, differentiated an implicit function and ended up with an implicit derivative, right? Our derivative in terms of both variables. Okay, hopefully we're doing all right. And for some reason I have work here. Let me get rid of that. I must have been testing out some different ways to do this, making sure my problems were all good. No. Okay, so let's try another one. We're going to, again, differentiate with respect to x. We're not going to manipulate this function at all, just take its derivative. So the derivative for x squared is going to be 2x, minus the derivative of 2y cubed would be 6y squared times the dy dx. And then the derivative for 4y is just going to be 4, and then again dy dx. So you're taking the derivative of this like you normally would, and then multiplying by a factor of dy dx. Taking the derivative of this to get the 4 like you normally would, and then multiply by a dy dx. Okay? And then on the other side, the derivative of 2 is just going to be 0. So differentiated all those terms separately. That's what our sum and difference rule says we can do. Now everything with the dy dx stays on one side, everything without goes to the other side. So in this one I just need to move the 2x over. So I know it's going to become a negative 2x over here. And these two terms are going to stay because they have the dy dx in common. We're going to factor that out. So I'm going to have a dy dx and then a negative 6y squared plus 4 equal to the negative 2x that I subtracted over, or the 2x that I subtracted over. And then, again, solving for dy dx means divide over that binomial. So we're going to say dy dx is equal to the negative 2x divided by the negative 6y squared plus 4. And this would be an okay answer, but because each of the terms in this fraction has a 2 in common, I'm going to go ahead and reduce by 2. So let's say dy dx is negative 1x over negative 3y squared plus 2. And there we have it. We differentiated implicitly. We got an implicit derivative. Okay, so we have two more examples, again, just to practice the process a little bit, and then to make sure we can, follow the next progression of steps where we're finding the actual slope of the line that's tangent, so using our derivative to actually find the slope, and then using that slope to actually write the equation. So a couple more examples here, so we can, again, go through the progression. Let's find the slope of the line tangent to this equation at the point 2, 4. Now, previously when we were doing these, we were just finding them at a given x value, and I went ahead in these and gave the whole point of tangency because we're going to actually need the x value and the y value, so you're welcome, gave you the whole thing. But same process, all right? Let's take our derivative. So the derivative for 3x cubed, that's going to be 3 times 3 is 9, so 9x squared minus derivative of y squared would be 2y to the first times a dy dx, and then that's going to be equal to the derivative of 8 is just going to be 0. So negative 2y dy dx, and we're trying to solve for dy dx, so I'm going to subtract the 9x squared over, and then I'm going to divide, so dy dx is equal to negative 9x squared over negative 2y. Now that doesn't necessarily reduce, but I'm going to go ahead and, like the 9 and the 2 don't reduce, but I'm going to go ahead and reduce the negatives out. So 9x squared over 2y. So there's the derivative of y with respect to x. Remember what that represents. That represents an equation for our slope at any point of tangency. Well, we're given a particular point here, so let's find the slope at this point. So at 2, 4 means plug 2 in for x, plug 4 in for y. So we're going to say slope here is going to equal 9 times 2 squared over 2 times 4. 2 squared on the top is 4, and that's 4, so those are going to cancel, but maybe you wouldn't see that, I don't know. You're going to end up with 8 on the bottom, and this is going to reduce. 4 goes into the numerator 9 times, and the denominator twice, so 9 halves. Okay, so there's the slope of the line tangent to this function at the point 2, 4. Alright, and then the last progression would be taking the slope and writing the equation, so let's try that on this last one. So we're going to find the equation of the line tangent to this function at x equals 5. Let's go ahead and start by finding our derivative. So this is, hopefully you're recognizing, a product of two functions, 4x and then y. So I need f prime g plus fg prime. So f prime would be 4 times g would just be y plus f is 4x, and then g prime, the derivative of y would just be 1, and then we get a dy dx there. And then that's going to be equal, or sorry, not equal. That's the derivative of this part here, okay? And now I'm adding on an x squared there, so I'm going to add on the derivative of x squared, which would just be 2x. And then that's going to be equal to the derivative of the constant here. Color code. The derivative of the constant is just going to be a 0. Okay, so I want to solve for this dy dx. I'm going to leave that on the left side of the equation, move the other two terms over. So I'm looking at 4x dy dx equal to, I'm going to subtract over the 2x and subtract over the 4y. The order you do that doesn't really matter. I don't know why I wrote those like that. Subtract 2x over, subtract 4y over, and then again I'm solving for dy dx, so I just need to divide by the 4x. So dy dx is going to be negative 2x minus 4y, all divided by 4x. Now this reduces, but I don't know that it's really necessary to do that because we're going to end up evaluating at a particular point anyway, but I guess we could. So divide them all the terms there by 2, so get a negative 1, a negative 2, and then a positive 2 here. So I want to find my slope now. This is my equation for my slope. I want to figure out what that is at x equals 5. I'm also going to have to know y, so I've got to find my point of tangency. Fun times, right? Now I'm going to go ahead and go to my calculator to help me out with this one because I know I'm going to use my calculator to verify my work anyway. So I have 4xy plus an x squared equal to 5. There's my graph. I want to figure out what's happening at x equals 5. So x equals 5, there's my point of tangency right there. So if I plugged 5 in for x, the resulting y into my function, the resulting y value would be a negative 1. So my point is going to be at 5 and negative 1. So you could also do that by just putting the 5 in here for x and putting the 5 in here for x, and then solving for that 1y that's left over. It's going to get you the same result. But we have a calculator, right? Let's not kill ourselves. So now we want to find this slope at the point 5, negative 1. So we're going to say our slope is, let's see, a negative 5 minus 2 times a negative 1 divided by 2 times 5. So that's going to be, make sure I plug that in right, negative 5, negative 2 times negative 1, 2. Okay, so on the top we have negative 2 times negative 1, that's positive 2. Negative 5 plus 2 makes a negative 3. On the bottom, 2 times 5 is 10, so our slope is negative 3/10. And remember, this is our point of tangency, so we're going to use those two to write our equation. And I'm running out of colors here, so let's go. Remember, it's y minus y1, so y plus 1 equal to m, which is negative 3/10, times x minus x1, and then we can simplify. So y plus 1 equals negative 3/10 x plus 15/10, which would be 3/2. And then subtract the 1 over. So y is going to equal negative 3/10 x. And if I subtract 1, which is 2 over 2, 3 over 2 minus 2 over 2 is going to leave me 1 over 2. Okay, so this should be the equation of the line that is tangent to this curve at the point 5, negative 1. So let's do it. Let's check our work. Let's do it. Let's check what we've done here. So the point, again, was 5, negative 1. That's the point we're looking at. And here's our equation. Y equals negative 3/10 x plus 1/2. And it looks pretty darn good. And I'm just going to zoom so you can see it. Try to zoom so you can see it a little bit better. It doesn't want to zoom, but you can see it. I'm hoping that line is clearly tangent to that curve at that point. Okay, so with the exception of this very first example where I tried to avoid using the quotient rule by just multiplying, that cross multiplying there, you're going to try to leave your functions in the form that they are so that we can practice this implicit differentiation. And it's the way I'm formatting the homework as well. So you're going to have one of these types of problems. Go ahead and cross multiply. I promise it's going to be way easier than actually using the quotient rule. And if you tried to do that, you're going to see it's pretty big mess. So this would be the only one. The rest of them, just leave them as is, differentiate as is, to practice this process, and then what we'll see in the next topic is applying the process to solve some word problems. Yay, your favorite thing in the whole world. Alright, so you should be good to go for your assignment, but as always, if you need any extra help, then reach out. Until next time, take care.